hard to understate the importance of equilibrium to the next couple weeks and to chemistry in general. So this is where we're going to be living, and so it's best to sort of start with a strong underpinning of what's going on. Now, up to this point, we've been talking about reactions that progress, where we have some sort of reactant progressing to a product. And we did our first order rate laws, or our rate laws, excuse me. And we did our rate laws, and what we saw is that, we start with so much reactant, and then the reactant sort of peters out, and eventually it all becomes product during the course of the reaction. And during this time, what we see is the product growing in. And we looked at a number of graphs like that, and this is depending on the stoichiometry. And we were able to build a sort of series of reactions that relate to this elementary steps that take place, that progress. And we talked about the energy difference between these two, or the reactants and the products, and separating these is some sort of activation energy. Now, what if, and here's a good question, what if this activation energy is low? Low enough that the products have enough kinetic energy and enough chemical wherewithal to progress the opposite way. What's to keep this reaction from moving in reverse? And so we can think of it, this reaction going to the products, but why can't we think of it as the products also going to the reactants? In some cases, this is what we actually see. We see a reaction that is progressing either forwards or backwards. And associated with each of these is their own particular rate. So we'll say the rate of the forward reaction, we'll just say is equal to Kr. Doesn't really matter what it is. And the rate of the back reaction, we'll call it the reverse reaction, is equal to Kp. If the two rates are equal, if the two rates get equal to one point, and at some point, as this reaction progresses, eventually it's going to build up, P is going to grow in, and P is going to get large enough that it's going to drive backwards, and then R will, and you end up with what we call a steady state system, where the forward reaction is happening at the same rate as the back reaction. And so what that means is these two quantities are equal then. And so they can be set equal to each other. And so we have, let's call this one K1 and this one K2. We have K1 with the reactants is equal to K2 with the products. You don't have to write this all down. This is just an example. Well, we can rearrange and solve for this, and what we'll find is that we end up with a statement that would look sort of like this, where we have a constant that is proportional to our concentrations. And these would be our concentrations at equilibrium. If these are steady states, these are constants as well. And so we now have a mathematical expression that explains reactions that proceed in both directions. And this is what we call our equilibrium statement. Right? They don't always look like this. This isn't as simple as it is. But we can write a generic expression that sums this up. Reaction A going to B, A going to B, in equilibrium, and we use a special arrow, double-headed arrow, to represent that this is an equilibrium, C plus D. For every reaction for every equilibrium reaction, the equilibrium constant, KEQ, will be equal to, unlike rates, now this is different than rates, different than, with a rate law, we never know what the rate is because it's based upon some elementary step that makes up the rate limiting step. But for equilibrium constant, every equilibrium constant is the same. The form of the equilibrium constant is always the concentration, though we can actually use other things besides concentration, but in this case we'll use concentration raised to its stoichiometric power times D raised to its power, all divided by B raised to its power A. So it's approximately proportional to reactants over the products. So the equilibrium constant K, and this is a capital K, is approximately equal to the reactants over the products. It has this form. Every single reaction is like that. So let's take a look at an example. 2NO2 going to N2O4. The equilibrium expression for this would be KEQ is equal to the concentration of N2O4 divided by the concentration of NO2 squared. And these are equilibrium concentrations. This is the concentration of those species at equilibrium. That's simple. Makes it quite trivial to write an equilibrium statement. Always products over reactants. So let's look at some of the aspects of the rate law. So we already looked at this reaction. 2NO2 is in equilibrium with N2O4, and that's equal to the equilibrium constant KEQ. Now we can express KEQ one of two different ways. We can write it as KC, where this is the equilibrium concentration constant based upon concentrations. Or Kp, where this is the equilibrium constant based upon partial pressures. The two are not equal to one another in all cases, but they're just two ways of representing the same bits of information. Usually when you deal with gases, you deal with Kp, and Kc is almost always solutions. And sometimes we just talk about a generic rate constant K because of the factors that I'll take into account later. Regardless of which form you see, they all have the same generic overall form. So the concentration in the above reaction, just call it Kc in this case, is equal to, again, products over reactants, N2O4, the concentration of N2O4, divided by the concentration of NO2 squared. Right? And this is a constant. This Kc is a constant. So for any given reaction at that particular temperature, it will be constant, which is very powerful, and we'll use that. Now let's just play a little game where we flip this reaction. So instead, the reactants, this is the products. Well, let's start off and just do a little formalism, talk a little bit of formalism. Right? if the reaction is progressing forward or backwards, it doesn't really matter. I mean, if this reaction was running in reverse, N2O4 would be a starting material, wouldn't it? That's true. But for sake of formalism and for the math, we always define the reactants as those materials on the left-hand side and the products all those materials on the right, regardless of how this reaction actually is progressing. We'll see situations where we would predict the reaction would actually be running in reverse, but that's not what we're gonna discuss right now. So we always define the reactants as the starting material, the one on the left-hand side of the double-sided arrow, and the product's always on the right. So let's flip this. Let's actually turn this reaction around and pretend that rather than 2NO2 going to N2O4, we were to try the reverse reaction, N2O4 being split into 2NO2. What would the form of the equilibrium constant be? So let's take a look at this example. So this would become equal to, not surprisingly, NO2 squared divided by N2O4. Divided by N2O4. So we flip this reaction, and what did we do to the equilibrium constant? The new equilibrium constant is now equal to the old equilibrium constant inverted. So whenever we flip the reaction, we invert the equilibrium constant. Mathematically, they have become flipped. So the relationship between these two reactions, we'll call this one Kc prime, is that Kc prime is equal to 1 over Kc in this case. Kc. So if we know the value of this reaction, we can, if we know the value of this equilibrium constant, something we can look up in a table, in fact, we can use it to predict the equilibrium constant for the reverse reaction. What about if we were to look at doubling of the equilibrium constant? N2O4. 2N2O4 goes to 4NO2. We could predict that, well, if we double this reaction, the equilibrium constant for this one, which I'll just call K double prime, C, would become equal to, in this case, 1 over Kc squared. Double the reaction. You square. Double the reaction, you square the equilibrium constant. Reverse the reaction, you invert the equilibrium constant. Well, here we both doubled and inverted. So this is just a mathematical game. Notice we can, again, if we look at the form of this, K triple prime C would be equal to NO2 raised to the 4th power, all divided by N2O4 squared. And if you compare these two quantities, you can see that how they are related. So numerically, we can solve for these. Again, Kc is often a constant. If we know what these values are, we can use this mathematical manipulation to figure out what those values are, and it comes in handy for certain calculations.